next is me, and since I need to prepare myself, I invited a guest MC. So I'd like to welcome Van Riper from Google and old coworker of me to introduce me. So please, all yours.
Hello. So this is actually my christening in the Go community, but I've actually been doing developer work for a long time. My name is Van Riper, by the way. I'm joining Kaz this week to work with the Go developer community, but for about 4 years, I was the program manager for the Google Developer Groups program. So if any of you are familiar with that program, you know that work. And that was when I used to work with Francesc. And let's see, what else can I do? Yeah, so I'm going to be around all day. Cass had to leave, but if you have anything you want to talk to me about, you know, our support for the Go community, please come and talk to me.
Thank you. Round of applause. Cool, so now I need my slides. Thanks to Google for emceeing too. Cool, so hi, I'm Francesc Campoy, and I'm also your MC. And I'm gonna be talking about machine learning in Go. Recently, you may have seen, I gave a talk at GopherCon about machine learning on Go, or how to use machine learning to better understand and better use Go. Today I'm going to be talking about the other side of the coin, which is how to use Go to do machine learning. And whether this is a good idea or not, spoiler alert, not really. But we're going to be talking about whether it's, I mean, it's early on, but I guess this, the goal of this talk is mostly like to show you a little bit what's around, what you can do nowadays, and then inspire you to contribute to the projects that are trying to change this to make Go a better language for machine learning. So in 1996, we had exciting times. It was very exciting for many reasons. One of them was computer scientists were sure that machine learning was going to be the thing. And that by in a couple of years, people will be talking to machines the way we do today, right? If you have, I'm going to try to wake all of your phones up. If you have Siri, or Hey Siri, or OK Google, or if anyone has Alexa here, which would be weird. But the way we talk to those today, they thought that it was going to be basically a couple of months, you know, because machine learning is easy. Unfortunately, that was not true. In 1996, it's when Deep Blue beat Kasparov playing chess. And this was huge. Everybody was like, you know, this changes the way machine learning works, like the way we see machine learning. Because all of a sudden, not only machine learning is kind of like a research thing that is kind of cute, but it's actually better at playing chess than any human being, which is kind of impressive. He was not impressed. You can see his face. He was not as excited as the computer scientist behind the project. In 2016, we have something similar. Lee Sedol, best human player of Go ever. He's amazing. Like, he beats everyone. And then DeepMind comes with this project, AlphaGo, with the whole idea of trying to play Go better than any humans. And this might seem like it's an easy thing to do, but actually, it is really not. I've never played Go myself. But basically, the whole idea is the number of possible games that number of possible plays that you have in Go is a different, completely different level than in chess. Chess is basically playing like tic-tac-toe compared to playing Go. So it is incredibly hard to play. So this was a huge challenge. And they won. And he was actually kind of happy about it. So this says a lot about like the difference between chess players and Go players, maybe. But he looked pretty excited about that too. So in 2017, things get even better. Because so the first version, so I'm going to be talking about the different versions of AlphaGo. So the first version was the one that, well, the first version that we saw playing against a human being. It was called Li Fan. And so Alpha Fan, I think. Fan. Oh, no, it's actually called Fan Hui. Okay, so because they were playing against Fan Hui, a great player. Not the best player in the world, but still really, really good player. And they were able to beat them, 5-0. Then they played against Lee Sedol, and they were able to beat them, 4-1. Then they created Alpha Master. And Alpha Master is able to beat, he was able to play against professionals, a bunch of them, and he was able to beat them 60-0, which when you beat someone 60-0, that's infinite anyway, so like you're just beating them every single time, right? And then you have AlphaGo 0. And AlphaGo 0, what they did is they made it play against AlphaGo Lee, which is the one that beat Lee Sedol. And they were able to make this win 100-0 against the thing that beat Lee Sedol 4-1. So that's incredible, right? And the thing that is incredible is the hardware. You might think that this is hardware-wise, right? Like GPUs, TPUs, improving the hardware, making it faster, and that would make sense. But let's see what it actually happened. So the first version was running on 176 GPUs. GPUs, graphical processing units, which are very useful for machine learning because you have matrices and vectors everywhere. So it's not that different to vector processing, to graphic processing. So you have 176 GPUs distributed across a bunch of different computers. Then you go to Lee Sedol, AlphaGo Lee, and it's only 48 TPUs. TPUs are TensorFlow processing units, or tensor processing units, rather, and they were created by Google specifically to run TensorFlow. So they're like machine learning hardware, specifically. So it kind of makes sense that, you have 48 of them. They're probably more effective than GPUs for this, so it kind of makes sense. They're still distributed across a bunch of computers. Next one is 4 TPUs, and that's connected to a single machine. So now you have one computer beating a human being at Go, 4-1, which is crazy. And the last one, also 4 TPUs. And so this is amazing, right? Like we're going with less hardware, we're still able to beat humans and to actually beat them even more than before. So it's not the hardware, it's actually the software. So machine learning is pretty amazing. Right now, the way they train AlphaGo AlphaGo Master, sorry, this one, was to play against itself. And after 40 days, it reached a level that no human being has ever reached. This is amazing. So yeah, machine learning is a thing. I work for a company that does machine learning, sourced. And I'm a VP of Developer Relations there, but before that, I was working at Google on the Go team. So my passions are Go, machine learning, so I decided to write a talk about machine learning in Go. Machine learning is great, Go is great. What happens when you put them together? So before we start talking about what machine learning, what kind of things you can do with Go in machine learning, let's talk about what machine learning really is. We have this definition by Tom Mitchell. I'm going to try to read. It's a computer program is set to learn from experience E with respect to some test T and some performance measure P. If its performance on T as measured by P improves the experience E, which rhymes, which is cool. But the important part is experience and task. When you're doing machine learning, you're performing a task, specific task. We're not talking about general AI. This is machine learning, not AI. There's some specific task that we're trying to achieve. And we increase our performance by experience, right? Experience means that we're going to be spending some time. Like we might spend 40 days training a model in order to achieve the accuracy that we expect. And finally, performance measure P. And this is really important. You need to know how well you're doing or how bad you're doing to improve. And this for machine learning, but in general, right? Like you need to have a framework that allows you to know whether you're doing good or bad. And not only that, but for machine learning, you also need to know in what direction is the best solution, right? So that's what we call a gradient. So basically it's like, hey, like out of 10, you got an 8. And if you want to have more, you should go that way, right? So that is the whole thing of machine learning. So the hello world of machine learning is MNIST. And MNIST is a data set that has all of these handwritten graphics, handwritten digits, and the idea is that they come with their labels. So you can see on the left, there's a label that says, oh, this is 0, 1, or up to 9. And then on the right is the prediction that the person that created this image, which is not me, did, right? So our job is to create a neural network, or, well, actually, any kind of machine learning device that is going to be able to predict that every single one of these bits, like groups of bits, bitmaps, correspond to one of those digits, and see how well we can do. So, machine learning, we have the task. It's recognizing the handwritten digits. The performance measure is how many of them we got right. And the experience is going to be, we're going to try to predict and then use gradient descent to improve on our predictions. Basically say, that was not a 7, looks like a 7, but it's actually a 1. You need to fix it. And try to repeat this over and over until we get to somewhere which the predictions are pretty accurate. So our input is that image, which looks like a bitmap, which is, I mean, it's a little bit more complex than this 4 right here, but basically that's the idea. And then our output is the 4. The other input we have is also, so these are, you can consider these as our inputs. We have the images and the labels, and our output will also, hopefully, be also a 4. But it could be a 3 or 2, well, probably a 9 is the closest thing you can imagine to 4. So how do you do it? Maths. I'm not going to get too much into the details of the mathematics, but this just to show you, it's actually pretty straightforward if you know some basic algebra. What you do is you have X is the images, which is just a matrix. An image is just a matrix of numbers, right? So we're going to multiply it by W, which is our weights. And then we're going to add another vector, which is the biases. And then that gives us our labels, Y, right? So this seems pretty straightforward, and it really is. And by learning, what we're doing is we're just changing the numbers in W and B. We're just tweaking those numbers until the result of that multiplication, of that operation, gets as close as possible to the labels we had originally. That's pretty much it. So yeah, the input, the weights, the biases, and our prediction. So that is the task. This is the performance, how we measure performance, how we measure the cost, actually. And it's a little bit more complicated, but basically what we're doing is computing some distance. Distance can be many different things. Every single algorithm uses a slightly different definition for distance. But the idea is that you have a distance between what you predicted and what you actually had to predict. So you could say, you know, a 4 and a 9 are 5 away. Why not? Actually, it doesn't work that way. You do it with vectors and distance and vectors and stuff like that. But the whole idea is that you are able to predict, to say how bad was your prediction. And 0 being, you got it right. We do that over all of the predictions, and then we divide it by m. So this is basically the average of how well you did. And this is our experience. So how do you use those two, the task and the experience, the task and the performance, to improve with experience? Well, it's the magic of gradient descent. And I'm not going to get into the details, but the whole idea is that when you have this, you can actually do derivatives of this, which means that you know where it's going. So given that, you basically are given not only how well you're doing, but also in what direction you should go to improve. So what you're going to do is you're going to say, OK, so how well I'm doing? Great, I'm doing 80%. If I want to do better, I need to do a step in that direction. You're going to do it again. You're going to run the whole thing, and then the next step. So step by step, you're going to try to get to the best possible prediction you could do with your model. And yeah, and that's math, so whatever. So MNIST tutorial. Where do you start? Well, the first step is, of course, you install TensorFlow, or you install Keras, or you install Theano. All of these are written in Python, or maybe deep learning for J, which is for Java, Spark, also in Java. You can also use Python, which I do not recommend. Or you can also use Octave, which is the open source version of MATLAB. I've used a bunch of these ones, and it's great. It works really well. But I'm a Gopher, so can we do this in Go? So what do we need? It's all about multiplications and additions. It's matrix multiplication additions. That's pretty much it. That's machine learning for us, right? So you need to be able to do multiplications fast. Also, you need to be able to read files, specifically read images, and then visualize those data sets in some nice way. And that's pretty much it. Like reading files, Go is perfect at that. image processing is actually really good with Go. Surprisingly, if you've never used the image package in the standard library, I invite you to try it. It works really well. So it is pretty straightforward. So we just need to check on that part of multiplying matrices effectively. So gonum. Gonum is the way to go, obviously. If you've ever used NumPy, gonum is to Go what NumPy is to Python, and it works really well. It is a pre-mature, I'm gonna say library. It's a bunch of packages. There's a bunch of different things that you can do. And it covers statistics and probability distribution, differentiation, integration, which is part of the things we're gonna be using, and also plotting. There's gonum plot is similar to matplotlib if you ever use that in Python. So you can do many cool stuff, many cool things with this. Cool. So for our problem, this is the mathematics we need to do. This the logistic regression. This is how you perform, how you compute how well you're doing in logistic regression. So you need to write this in Go. And in order to write this in Go with gonum, you would end up writing something like this. And this is not bad. It is relatively easy to follow. Basically, you're multiplying things, and then you're adding them, and subtracting, and stuff like that. It's not super complicated. But I don't like it. And I don't like it for a very specific reason, which is here what we're doing is we're creating H, which is the matrix. We're going to be keeping all of those results. And we are reusing that matrix over and over to reuse the memory, which is good because you want to allocate as little as possible. But also that means that you are destroying the previous results all the time, which means that this is not immutable at all. And many weird errors will happen. So for instance, one of the errors I had was in one of the first versions I wrote, I was actually modifying the matrix X. So I was actually modifying the images while trying to predict things. This happens. And now what you're doing is you're predicting something on a data set which is not at all what you thought it was, right? So mutability is kind of dangerous, but it's the price to pay for performance in this case. So that's great, but not much. I am not very happy with the API specifically. The mutability kind of bothers me. So what I did is I reinvented the wheel, and I made it way slower. So the idea behind this package, mat, is to implement matrix multiplication in a way that makes sense from an API point of view. It's something that is easy to use and hard to misuse, which is, they're both really important for APIs. And hopefully works fast. So we'll see how well it works. It only supports float 64, because that's what I use. And if you want to support float 32, send a PR or something. It's pretty straightforward. It's open source. I do not recommend using it. Before anyone comes to me in a month or so going like, hey, we're using this in production, do not use this in production. Okay, so with that library, the code becomes a little bit simpler in my opinion. It resembles more what you would expect. You have this product of two matrices that returns another matrix. Then you can do the prediction of that, multiplying x and theta minus y. So that's similar to the formula that we wrote initially. It looks more like the mathematics, in my opinion. So I am pretty happy with this. So let's try it. So I wrote this program, which is here. And the program what it does is it has all of these images, and that is the input, the labels and the images. So now when I press enter, we're going to start training this matrix and learning better what is the predictions. And after 30 seconds or achieving 100% accuracy, it will stop. And it stopped. We have training accuracy of 100%. Yay, our model is perfect. It's able to predict every single image correctly. That's great, except that I'm cheating. Because I'm actually totally cheating in here. Wait, here. Where I'm saying, you know those 60,000 images you had? Let's do it with 100 instead. So that's not okay. Because of course, predicting a fewer number of images is always easier. So let's try to do it with the actual number of images. So we got that. I press enter, and now we start. Yeah. So this is the beginning of the first iteration. Yeah. No, I'm going to wait. I will make you wait. Okay, there you go. Okay, so 15 seconds. 15 seconds, which is good, but also really bad. 15 seconds to spend on iterating only once, taking into account that you're going to be doing this thousands of times, it means that this is going to take weeks to train. So also the accuracy we reached was an astounding 39%, which is better than random, but not much. So yeah, that is not great. But this is the package I wrote, right? So if we go to fit, actually optimize, I think it's here, yeah. So one of the things that I did here was that matrix product, I used the product function that I defined myself. So let's see how that's done. It's just a loop, literally. It's like a loop inside of a loop inside of a loop. So that's why it's so fast. And basically, we're just computing all of this, and then that's it, right? Like, this is the basic naive algorithm, and it works. Not fast, but it works. So the next step is, this is Go routines, yay. So I'm gonna create a Go routine per pixel in the output matrix. So that's why we have this Go routine there. So now we have, rather than having cubic, we have quadratic, but also every quadratic is in a different Go routine. So we spawn something like 60,000 Go routines in this case, which is fine. I've done more than that, and my computer didn't burn, so it should be okay. So we can change that by changing this to parallel product. Okay, so let's see how the timing works. Once more. Yeah, okay, so first iteration. That was 15 seconds before. Now it's 7 seconds. Yay, okay, perfect. This is way faster, but still not fast enough. This is definitely not fast enough. And if you try to improve this, you can have lots of fun in trying to use pprof and everything to try to minimize exactly how many cycles you're spending on every single multiplication. And that's cool, but what I decided to do is like, okay, gonum might not have the best API in my opinion, but they definitely have performance. How do they do it? And it's actually kind of interesting. So here there's a mul function. And this mul does something similar. It's not on float, it's not on matrices, it's on slices of float 64s, but that's pretty much the same. So I'm curious about how this is done. Let's see the code. And no, that's totally not what the one I wanted. It's actually, I think it's dot, the dot product that I wanted to do. Yeah, this one here. Dot, yeah, so dot, what it does is it does a quick check on something, and then it calls dot unitary. So that is F64, so let's go there, F64. So let's open that. And the new Chrome is awful. I don't know why they did that, I'm not happy. So let's do godoc.org. I was supposed to have that open, but I forgot, because I'm emceeing, so you're gonna be nice to me. Okay, so that was dot unitary. So dot unitary. Cool, so let's see the code for this. Oh, there's no code. And this is really interesting, because what is going on here is actually, you have the stubs, which are the function definitions, and then you have AND64.s. So what we're doing is actually we're using assembly. And this is a very smart thing to do, because in this case, we know that this one, let me put it up a little bit, this is for AMD64. We know the architecture, so we can use specific instructions that will be faster than us writing the code. So that's what they do. So I'm gonna do the same. So that is when we go to blast product. And this is calling blast64, which is something like basic linear algebra, and the S stands for something, I'm sure. And now we're going to change that to use this. So let's see if using assembly, we can get performance that are closer to the performance of Python. Because Python also, by the way, they totally do this too. Python, the matrix multiplication is not written in Python. So let's see. We went from 15 to 7 to 1 second. This is really good, but still far from being good enough, unfortunately. But this shows you a little bit, like let's see in 30 seconds where we can reach and see the result of what are the things that we're able to predict, what are the things that we failed at, and see whether that kind of makes sense. So we have 9 more seconds, 8, 7, 6, and I think I implemented the timeout. Yes, I did. Okay, so it says this was supposed to be a 5, and we predicted it was a 3. Personally, we would do the same. This was a 5, and we predicted it was a 1. This was a 9 if we predicted a 1. So this kind of makes sense, right? Like the fact that we're failing the predictions here, it's not crazy, because like, to be honest, this 4 could be a 9 too. So our model was actually pretty good. It is far from being perfect, but also trained it only during 30 seconds. So if we were able to train this for long enough, we get accuracies that are decent. Not amazing, because I'm using a very, very simple model. I'm not using neural networks or anything like that. But Go is able to do things like this, which is pretty cool. And actually, I was pretty surprised about it. So all of the things that I showed, they're open source. So if you want to check them out, you have the math package, which, again, do not use. Thank you very much. If you want to use the one that's like the Blast product, that's okay, but anything else, do not touch. We also had GoML, which is the one that contains the main program that I was running here with all the data and everything. And ImageCAD is the one that I'm using for plotting the images directly into iTerm too, which looks pretty cool. So, gonum is actually great. I do not like the API, but as the basis of the foundations of what we're going to be able to build with machine learning in Go, is a great starting point. So if you've never used gonum, I invite you to try it, and actually to also contribute to make it even better. While preparing this talk, I actually contributed and made my first contribution to it, so now I'm a contributor too, which is great. It was literally 1 line of code, but it still counts. So what's in the future? Well, this doesn't use GPUs. TensorFlow, AlphaGo uses GPUs and TPUs. We're not using neither of them, right? So could we use GPUs? Well, that'd be cool, but it's something that I'm not gonna have the time to implement myself. It's actually kind of complicated, right? So maybe what we want to do is just port TensorFlow, like rewrite TensorFlow in Go. And that sounds like a crazy idea, because so much work behind it. But it's something that part of the community is already building. There's a package called Gorgonia that kind of tries to do this, and it works quite well. The documentation is not perfect, but it's a pretty young project, so it totally makes sense. So I invite you to try it if you're trying to do anything machine learning related in Go. The other option is to reuse TensorFlow, right? TensorFlow is a C thing that has a nice Python packaging. We could do the same with Go. We could do the packaging with Go and use CGO to call TensorFlow. And this is something that is done, kinda. You can go to TensorFlow and actually have it here. The package TensorFlow exists for Go. And unfortunately, it only allows you to take a model that has been trained and do predictions from it. You cannot train a model with Go yet. But according to the product manager at Google that I bothered many times, he says it's coming. He said it's coming for like 6 months. So, you know, like it might come eventually. So if you want to learn more about machine learning in Go, I recommend that. Okay, it died. So I host this YouTube channel just for fun. I'm going to have a bunch of videos specifically about machine learning in Go. And also I do it on Twitch, where you can see me trying to use TensorFlow in Go and fail miserably at it for hours. It is fun for me, and I hope for other people too. And that's all. Thank you very much. Okay, now back to emceeing. So we have no time for questions because we're already ran 2 minutes late. So we're going to take another break of 18 minutes this time, and we'll be back at 11:30 for a talk about tracing Go with Jana, which is somewhere around. Have fun and see you in 18 minutes.